For attending this presentation on 4 little known tools to jumpstart your systems thinking. I'm Joe Casa. Why do you need those tools? Well, you need those tools to understand and manage complexity. There are 2 types of complexity. The first one is real-world complexity, in which the elements of the real world are related in some fashion. This complexity is not reduced by appropriate abstraction, it's only hidden. And then there's what I call artificial complexity, arising from either poor aggregation of the elements of the real world, that in most instances should have been abstracted out when drawing the internal and external system boundaries. And I'll explain some of that in a moment. You use these tools to manage complexity by reducing artificial complexity. Do you realize there's a dichotomy between 2 different groups of people as to how they handle complexity? The first one says we need to develop new tools and techniques to solve these problems. And you find examples of this as far back as 1976 in a PhD dissertation. The problems posed by complexity seem to be unmanageable. Or the systemic reason for the challenge projects in the Chaos 1998 study was their inherent complexity. I'm sorry, it wasn't. I read the same reports, and the conclusions I came to was that the challenge projects failed due to poor management. Or this one, for all practical purposes, adequate testing of complex engineered systems is impossible. Well, there are a lot of them working. And there's the complexity primer for systems engineers, created in Incosi in 2013. And the quote I gave in session 1, the world is complex, so our thinking should be complex as well. But on the other hand, these complex problems are being remedied successfully. A national railway network, organizing the timetables, the maintenance, complex problems. Cruise ships. Cruise ships deals with the ships, the servicing and maintenance of the ships, the advertising, the marketing, the entertainment, arranging for shore trips, tremendously complex. And what's more, the schedules can be arranged up to 2 years in advance. Airlines, running flights around the world, making sure that when on an airplane requires servicing, the airplane and the part end up at the same location, dealing with passengers, dealing with baggage, dealing with all sorts of things. Or international air freight forwarding companies, automatic rapid transit systems, banking via the internet, and the automatic teller machines. I log on to my bank account. My bank is in a different part of the world. It sends me a text message. I respond to the number it gives me, and then I can get into the account. Hospitals, oil rigs, and so on. All these complex systems are working. These people don't understand why the other group has a problem. Lots of people think that systems thinking is using causal loops. Well, back when I did this research, I looked up the definition in 2 different dictionaries and couldn't find anything. But there were many variations on various websites. And basically it was something like this. There's something. There's a cause, and there's an outcome or an effect. And we call that cause and effect. You push the light switch, and the light comes on. Cause, effect. But a causal loop goes a little further. It provides feedback. So the effect also goes back to the input. And sometimes there's a delay. Sometimes it's instantaneous, sometimes it's a delay, both in cause and effect and in the feedback. If I punch you on the nose, you will feel it instantaneously. Oh, let me tell the story. Years ago, we bought a house, and the house was on 2 levels, and there was a chairlift in the house. And so we tried turning the chairlift on and off, and nothing happens. So we thought it was broken. We didn't need it, so we just left it alone. And then one day we had a guest in the house who was playing with it. She sat in the chair and pushed the switch, and for some reason she waited, and then she started moving. So there was a delay built into it. And we use this delay in control systems. Many systems thinkers talk about laundry list thinking. This comes from the work of Barry Richmond. And I copied this from Derek Hitchens with his permission. Here are some of the factors that affect morale. Low pay, poor conditions, lack of recognition, and poor prospects. And he calls it the laundry list mentality because it treats each contribution of the list item as separate. It overlooks their interrelationships, but they forget it's the first step in creating a causal loop. Because you can't create a causal loop unless you know what the inputs are. So you've got to have that list of inputs. And by the way, if you've never seen a laundry list, this is an example of a laundry list. You see the laundry items, you see how many items were supplied, you see the prices, and the laundry place totals it up and tells you what it will cost. So how do you create a causal loop? Carefully. Obvious answer. You look at some of the factors and you look for relationships between them. So in our morale example, we have recognition and attitude about work. When people are recognized, their attitude about work improved, they work better, so they get more recognition, positive feedback. When performance and prospects, as performance goes up, people's promotion prospects improve. And as their promotion prospects improve, they get promoted, then hopefully their performance will go up. Or conditions, attitude about work, performance, and revenue, and you can see how that happens. Or here's another one, pay, satisfaction, attitude about work. Not every element is related to every other element. Living and non-living systems are full of negative and positive feedback loops. Negative feedback regulates and seeks goals. Positive feedback causes runway or multiple points of stability. And all the examples here are positive. And I noticed after a while that I was teaching this, and then when I asked the students to create some causal loops of their own, all the causal loops they gave me were positive. None of them had anything negative in them, so I changed the example to include some negative ones as well. And then you create a composite causal loop by adding them together. You see the things that affect attitudes about work, performance, organizations, revenue. The revenue outputs go to pay or conditions or prospects, and you create the loops. One of the things causal loops do not tell you is the strength of the relationship. For example, how much of the organization's revenue goes to pay, how much goes to conditions. That's a decision the organization made. But what it doesn't tell you is the relative benefit of, if you increase the pay, how much do the prospects go up, or if you increase the work conditions, how much does the morale go up? That comes from some other information. On the other hand, you can get too carried away and create very complex causal loops, something like this, as General McChrystal said when he was presented that in a briefing. When we understand that slide, we'll have won the war. There has to be a better way. And those 4 little known tools that I'm going to teach you now are, in my opinion, the better way. The first one is keep it simple, student. The second one is the principle of hierarchies. It's been used for thousands of years to manage complexity. And then 2 I developed called holistic thinking perspectives and active brainstorming. Keep it simple, student is a basic tool for managing complexity, but it's often violated, particularly in drawings, and I'll show you an example in a moment. It's usually created from a brain dump, and they put too much in a single drawing. And it contains information from several perspectives. And it's generally because people are trying to use one drawing for multiple purposes where they should be using several different drawings. Remember Miller's rule? 7 plus or minus 2 chunks of information is all that the human brain can handle. So why put more in the drawing? You need to think through the information you're presenting to yourself and to other people and sort out what's pertinent to the issue and abstract out what isn't. And we call that, in engineering, sort out the signals from the noise. So how do we use KISS? Well, we view the situation from a number of different perspectives and temporarily ignore anything not pertinent to that perspective. For example, the holistic thinking perspectives. There may be other sets of perspectives. In fact, the continuum perspective that I'm going to show you says there probably are. Use only 10 or fewer objects in view at any one time. Group the objects into bigger objects, and that's the principle of hierarchies. Principle of hierarchies. I'm just giving you an introduction to it. There's a lot more detail involved. The principle of hierarchies can be summarized as follows. All systems of relatively stable character display hierarchical organization of levels. Some exist within metasystems or containing systems. Systems contain subsystems. A subsystem of a system may be a system with its own subsystems. What a system does or will do is defined in the metasystem. The properties at any level are different to the properties of other levels. The properties at any level consist of the combination of the properties of the subsystem components in the next lower level, and the emergent properties, the interaction between the subsystem's components in the next lower level. And when looking up from the perspective of the next lower level, or when creating the system, some of the emergent properties at any level can be predicted and some of them can't. So let's look at emergent properties. The first set of emergent properties are known, observed, or predicted. They're desired. That's the purpose of the system. That's what we design the system to do. There's undesired based on experience, and these should be prevented, designed out, or mitigated, or compensated for. Electronic engineers know that certain circuits will oscillate, and so they put in components designed to prevent or mitigate the oscillation. The same thing happens in mechanical components. For example, we have shock absorbers in the car to give you a smooth ride, because one of the undesired emergent properties of a vehicle is it shakes around due to the interaction between the vehicle and the road. And then there's the don't care. We know about this emergent property, but we don't care. It doesn't have any effect. And then there are some that are unknown, which once discovered turn out to be undesired or serendipitous. I never knew the system could do that. Wow, I love it. Or the undesired ones, once they become known, they're treated like the known emergent properties. And again, we didn't know the system would do this when we built it, and it doesn't affect us, we don't care. And the third set, a disturbance introduced into the system at any one level can reverberate in other levels. A system of interest is made up of two or more of the subsystems of the system. There's my system. It's got 5 subsystems, and there's my system of interest, and the boundary of the system of interest is crafted by the observer for a purpose. And you can see that the subsystems 1, 2, and 3 are inside my system of interest, 4 and 5 are not, so they're grayed out. And this was discussed in session 0, the BCS presentation. So how do we use this? Well, here's an example of the real world. We've got components, they're interrelating to each other, and then there are more of them that go off screen. And what we do is we group them into subsystems in some way. Here are the subsystems that have been grouped together. And what we do is we group them, right? 1, 2, 3, 4, 5, 6 subsystems. So if we ever want to look into what's going on, we look into that one, then we look into the next one, then we look into the next one, and then we look into the next one, and then we look into the next one, and look into the next one. It helps us find Waldo or any other activity we need to do. This whole concept is fractal, because I can take these subsystems and draw my system boundary around it, fill it in, think of it as a black box or an orange egg, and zoom out. exactly the same way as we did in the BCS presentation in session 0. Once we've zoomed out, we can see the adjacent systems, and we're exactly in the situation that we were before. If I want to draw it as a hierarchical chart, I can show it this way: metasystem, subsystem 1, 2, and so on. If we ignore the principle of hierarchies, we create something like this. It creates artificial complexity. It ignores Miller's rule. It combines hierarchical and operational perspectives. There are 3 levels in the hierarchy in the drawing. There are missing links. It's ambiguous because some of the links don't go into the containing circles, so you don't know where they're going to end up. And in Cosey's case, this is wishful thinking. Now let's look at the holistic thinking perspectives. When we're thinking about a situation, trying to understand it, we need to look at it from different perspectives. There's Sherlock in the middle. He knows that there are blind spots. He can't see through the black ball. So what does he do about it? Well, he moves to another point and looks from those perspectives. And he knows that there are blind spots there as well, but if he chooses enough perspectives, he will see the whole thing. And he's also smart enough to know that he has to go outside and look at it from a number of perspectives on the outside. And he's just as smart to know that he's got to turn around and look out from the system and understand its role in the containing system. And he tries to understand the role of the system in the containing system. Tim Mackley and I at Cranfield built on the work of Barry Richmond and created the 9 systems thinking perspectives. But then we realized it was more than systems thinking, so after a while we changed the name to holistic thinking perspectives, and I discussed that in session 1. So the holistic thinking perspectives allow us to look at a situation, big picture, operational, functional. The big picture and operational perspectives are external, functional and structural are internal, generic, continuum, temporal are progressive, and the quantitative and the scientific perspectives are what I call the remaining perspectives. The first 8 are descriptive in that we're observing what's going on. Then we do some critical thinking. Out pops the answer, the solution, our thoughts or whatever, and that is the scientific perspective. You use these partially, but you may not realize it. For example, if you're modeling an organization, you will create a hierarchical organization chart. If you're doing a process flow model, you will draw a process flow chart. Use different symbols. And in some organizations, when I'm trying to map the organization onto the process flow model, it's really trying to put a square peg into a round hole. So which perspective is needed? Well, it depends on the problem. If the problem is external, then we use systems thinking and how the object relates to the other parts. If it's an internal problem, we use reductionism. You have to look at how the object functions. If we want to come up with solutions, then we look at the progressive and remaining perspective. The external and the internal perspectives help us understand the situation. The progressive and remaining perspectives help us conceptualize solutions. Here's an example. Consider a camera. The big picture is where the camera are used and for what purpose. Operational deals with capturing images, transporting them, viewing the images, adjusting the settings, and charging the battery. Functional is how the camera works, how it captures the image, how we retrieve the image, what's involved in deleting the image, exactly how does the battery charge. Structural deals with the camera body, the lens, and the other physical components. Generic are other image capture methods such as painting, sketching, and so on. The continuum perspective may be different types and models of cameras, different materials used to construct the camera, different types of lenses, and so on. The temporal perspective would deal with the evolution of the image capturing media from photographic plates to film to solid-state memory. It reminds us that the way it was done in the past is not the way we're doing it now, and will probably not be the way we'll do it in the future. And the quantitative perspective gives us numbers, number of pixels per inch or centimeter, lens characteristics, the grain of the film, the cost, and so on. And the scientific, the output of what we're viewing depends on the problem or the issue. Well, let me give you an example. If the problem is related to understanding how a camera works, then we use the functional and structural perspectives, and our system contains the camera as a closed system of interest. When we're trying to understand what it does, for example, capturing images, this is the operational perspective, and our system contains the camera, the operator, and whatever is being photographed, if it was a film camera, as a closed system of interest. If we're trying to understand what happens to it, for example, transporting the camera, then we use the operational perspective, and the system contains the camera, the operator, and the camera case as a closed system of interest. If we're trying to understand what happens to it, for example, recharging it, again it's the operational perspective, and now the system contains the camera, operator, and charger as a closed system of interest. And notice how the system of interest boundary changed. And this was discussed in session 0. When I was writing the 4th book in the series, I had the idea to go through the manuscript and see how many times the words of each perspective showed up in the manuscript. So I went back to the PDF files and did a word search, and I noticed that in the Systems Thinking Toolbox, generic and continuum came up much more so than big picture, operational, functional, and structural. Because the toolbox was not only giving tools for gaining an understanding, it was also having tools for coming up with solutions. In the project management book, operational and functional show up because that's what managers are doing, and generic and continuum show up as well, much more so, because it's also discussing solutions. In systems engineering, look at that operational hit. Because systems engineers are concerned with creating systems that will operate and thinking about how it's being used before they actually create the requirements. And then there's a functional and structural perspectives when they get into the design. And again, generic and continuum are important because they're looking for solutions to the problems they're facing in the design. And in risk management, you see a lot more functional and structural, because we're looking for risks associated with the functional and the structural. A lot more quantitative because there are numbers associated with each of the risks. And since risks are events that happen over time, you can see that the temporal perspective mentions shot up an awful lot. If you'd like to see more examples of the holistic thinking perspectives, then I've got a presentation coming up on Can Systems Thinking Improve Your Sex Life? It's in session 6. Don't miss it. And I guarantee it won't be what you expect. Or how about systems thinking as it applies to systems engineering? I gave this presentation to the Nkosi Chesapeake chapter in 2021. You can find it on YouTube at the link shown. Or applying systems thinking to the 10 Commandments. If you're Christian or Jewish, have you ever actually thought about the 10 Commandments? There's a YouTube video in which I gave that presentation in 2020. If you watch that video, you will find the forgotten or the overlooked commandments. You will find that there are actually more than 10 commandments. So a good question to ask your clergyman and get yourself into trouble is, how many commandments are there in the 10 Commandments? And now the last tool, active brainstorming. You've probably heard of brainstorming. It's a technique for ideation in small groups that was written down in 1963. And there are lots of variations. The rules basically are think up ideas, no criticism of ideas, go for large quantities of ideas, build on each other's ideas, encourage wild and exaggerated ideas. So in the various variations of brainstorming, the meeting begins, the roles are identified, who's the facilitator, who's the scribe, participants know who they are. Somebody presents the problem and any further explanation if it's needed. The brainstorming session begins. Ask participants for their ideas. All participants present their ideas and the scribe records them. Participants may elaborate on their ideas to ensure clarity. There is no discussion or criticism. If no ideas are forthcoming, the facilitator might do something to trigger ideas, and then the brainstorming session ends. Then the ideas are categorized or sorted in some way, and duplicate ideas and obviously infeasible ideas are removed. They're not actually thrown away. They're saved because one day they might be feasible. And then the meeting ends. Well, active brainstorming begins when the brainstorming session ends. The way it's done is you take the holistic thinking perspectives, and from each perspective you ask the Kipling questions: who, what, where, when, why, and how. And in the beginning, when you're first learning to use this, you go around in sequence, and after a while you can jump from one to the other. And I provide you with this cheat sheet, an active brainstorming matrix. Sherlock is moving around, asking the questions as I speak. You ask the questions, and there may not be an immediate answer to every question. If nobody can answer the question, that means further research is needed. And if somebody says, I think, then somebody better confirm. So at the end of the meeting, there are action items for who does the research and so on. This is an input tool, not a storage tool. Don't put the ideas back into the matrix. If you do, and I have noticed people doing it, they tend to argue about which box the idea should go in rather than focus on generating new ideas. Typical operational perspective questions include: who's going to operate it or administrate it? What do they need to operate it? Under what conditions will it be operated? Where will they operate it? When? Why? How? Even how will they gain access to it? And generic questions might be: who has a similar problem? What's this similar to? Does this remind you of? What applies to both situations? Where can I find a similar situation? Will there be a similar situation? And we use active brainstorming after the flow of the initial set of ideas stopped. Don't interfere with the initial free flow of ideas. Don't force ideas into the HTPs during the initial thinking session. Do it later as appropriate. And don't force the ideas into the HTP during active brainstorming. Do it later as appropriate. Capturing the ideas and sorting the ideas are two separate tasks done at different times. The first time I ran this in a class at National University of Singapore, these were the results. There were 7 teams. They did a brainstorming exercise, and you can see the number of ideas there. And then they did an active brainstorming session, and this was the first time they'd been exposed to it. And you can see that the number of ideas went up phenomenally. Team 7 was just too lazy to count. So in summary, I explained to you why you need the tools. You need them to manage complexity. You need them so that you're on the side of the dichotomy that says, complexity, what's the problem? We can deal with it. I introduced 4 little known tools: Keep It Simple Student and the principle of hierarchies, and these have been in use for a long, long time, thousands of years. I also added holistic thinking perspectives and active brainstorming. And I have a lot more information and details on this that I can make available to you. Thank you for listening, and I will now return the session to the moderator.
Thank you, Joe. Interesting coverage of some of the ways we can think about the problems that we are addressing and trying to keep them constrained so we can hold them in our heads. There we are. I don't see any comments at the moment. If anyone has one, you can feel free to unmute yourself. And let me take another look into the chat and see if there's something topical at the moment.
So if I can, because it's in the chat,
Hi.
I was wondering for the 2 sessions, what fraction of ideas were immediately usable using your definition of you don't throw them away, but some get binned for later in the 2 different approaches that we took?
It wasn't 2 different approaches. It was first do the brainstorming, then do the active brainstorming. It was an academic situation, so the problem was contrived.
Okay.
So they didn't actually go into the sorting of the ideas. They just counted the number of ideas.
So I presume you looked at the responses?
Yep.
Would you have a sense for which of the 2 approaches produced a higher quality of responses?
About the same.
Okay.
That's my memory. And each time it's used, it's about the same. And sometimes the ideas and observations are wrong. For example, I noticed some people are wearing headphones and some people are not. So I can draw a conclusion that says the people who are wearing headphones are so full of ideas in their head that they've got to wear the headphones to keep them in. And I won't say anything about the ones who are not.
Good. Does that cover an answer for you?
Yeah, it does.
All right. Good.
I've used a number of variations myself. I just.
Mm-hmm. All right. Pascal?
Yes, thanks, Bruce. Mine is just a comment and then a short question. The comment is to share my experience. I did use active brainstorming a few times, and I found it very useful in terms of broadening and deepening your understanding of the situation that is at stake. Just a testimony for my side that the tool works. The short question is we've seen like 4 prophets given us 4 tools, but we know in system thinking there's many other tools like the soft system methodology, the iceberg methodology. You will find out that maybe the quality function deployment is also a system thinking tool. Is there any particular reason why prophets focus on these 4 and not mention anything about the others? If I've not missed something.
I only had 45 minutes.
Okay, all right.
If you want to know about other tools, then I have a great book for you to read, The Systems Thinker's Toolbox.
Okay, noted.
Tools are mentioned there. Paul Newton put a reference to Barry Richmond's 8 critical thinking skills. And Barry Richmond's work is really good. It's practical, it's usable. A lot of the systems thinking literature doesn't help me use it. There's an awful lot of what, but very little how. And it was Barry Richmond's how that his 7 streams looked at them and said, yeah, that's great, but we need to tweak them a little bit. And that's why we stopped it at 9 because of Miller's rule.
For the people who have used the active brainstorming approach, is there an advantage or a disadvantage to trying to get everyone to sort of think on the same, with the same hat, I guess, if you want to go to the hat analogy, at the same time? Or is there more advantage of having people going off in their own directions of either interest or fancy, I guess, and then trying to combine that information?
Oh, you find that you'll ask a what question from one perspective, and it will generate ideas that come from all the other perspectives. Depends, and as Kerry pointed out, you have people from different disciplines. Kerry pointed that out in the previous session. You have people from different disciplines with different backgrounds in the session, and the ideas bounce around all over the place, and the facilitator just asks another question when the discussion ends.
Mm-hmm.
I do find just a slight change to brainstorming that's worked better for me, is that years ago when I was introduced to brainstorming at, I don't know, was it school or uni, often the topic was unknown until you got into the session. And they put that as part of the brainstorming. Now I don't do that. If depending on the topic, I will send it out to people in advance so they can think about it. And then when they go into the meeting, then I generally get more people speaking because everyone's had a time to think, because everyone thinks at different levels. I don't want group think. I don't want the extroverts to take over unintentionally, etc. So I tell them I put the topic out. I said, we'll discuss it. Go away, either do your research or don't. It's up to you. But come to the meeting. Yeah.
Yep, that is excellent. I even generalize that. And I sort of teach anytime there's a meeting, the agenda should be posted ahead of time to allow people to think about what's going to be discussed. Okay, Paul says he got the titles wrong. The Thinking in Systems Thinking, 8 Critical Skills. There is, when you look at the definitions and what people talk about in systems thinking and critical thinking, you find that there's overlap. And you look at different versions. I went through this with the problem-solving process. There are you can look up various descriptions of the problem-solving process. But if you break them down into their functional components, you just see that they are different arrangements of the same generic process, sometimes leaving something out. So some people think that problem solving ends when you've conceptualized the solution and they don't really have to make it happen. For other people, the problem solving process includes creating and verifying the solution. Same with system thinking. I think if what I talked about in the other session was the different types of thinking, I think if we went back and looked at what each author meant by the different types of thinking, and we put them into an n-squared chart or whatever tool one would use, we could then answer the question why systems thinking wasn't mentioned in the 3 websites that I cited. It might be included. Or those people weren't dealing with problems in which they had to use systems thinking.
Or they couldn't understand what the definition of systems thinking was, so they just didn't use the words.
Right. There are a lot of people who are doing it, but they don't realize they're doing it.
So, Joe, systems thinking in your thought of definition, is it like problem solving that really encompasses a whole range of analysis and solution steps?
Well, system thinking to me means systemic and it's systemic and systematic thinking. So it's thinking about the system systemically. And I do that using the active brainstorming, holistic thinking perspectives approach. That's helped me a lot. And I even used that 50 years ago in what IBM called joint develop, JIT, whatever it was. And I've forgotten the question, sorry.
Oh, it was a question of the breadth of systems thinking in relationship to your thinking of problem solving, sort of encompasses both the analysis and synthesis piece.
So the systematic part is going through the active brainstorming, active brainstorming, sorting out the ideas. And some of the ideas will relate to the problem, some of the ideas will relate to the solution, sorting the ideas into idea storage templates that I use, and then planning the solution and then actually realizing the solution. And in order to get away from that, that's why I talked about using the systems approach, looking at problems from internal or external perspectives. And if you do it that way, you find that reductionism and systems thinking are pretty much the same kind of activities. So it gets away from the problem of reductionism and systems thinking. It gets away from all the difficulties with the definitions of systems thinking. It just says, if the problem is internal, go up to the meta system level and define the system of interest and deal with it. If the problem is internal, then you're at the meta system level and you define your system of interest and deal with it, like the bus won't start in the morning. If the problem is external, use the principle of hierarchies. Go up one level in the meta system, define your system of interest and deal with it. Same thing.
So is it the finding the problem, or is it the dealing with it part that is associated with the definition of systems thinking? I think that's sort of where my question is, and so far you've weaseled around that.
Systems thinking is generally systemic thinking, where you're thinking about this. You use it to gain an understanding of the system. But when you're trying to conceptualize the solution, you also use it to understand your conceptual solution.
Okay. Mm-hmm.
So you use it in both places. You use it in the traditional original approach of gaining an understanding of what's going on, but you also use it when you're trying to conceptualize the solution before you can realize it.
Yeah. Oh, okay. So that's a little different than I thought where you were going to end up, because I had sort of jumped ahead to it actually being an analysis mechanism, and you're analyzing the proposed solution using systems thinking, which makes it again an analysis technique rather than a synthesis technique.
When you're designing your system, you're designing for the emergent properties as well as the properties of the individual components. So again, you're gaining an understanding. So you're using synthesis there. And so systems thinking helps you there, because you have to look at your conceptual design and you have to think, will it do what I want it to do, or what the customer needs it to do? So
does anyone else have an observation or comment on this view of I guess we're really in engineering at the moment. So does anybody have a view of that from engineering, or can you translate this into one of the other disciplines?
I would like somebody really to comment from a different discipline, because I grew up in system as an engineer, electronic engineer, and then a systems engineer. And it's only when I started reading outside my discipline that all these questions came up. And I found that I could be very innovative because by having looked in other disciplines, I could look in other people's boxes and come up with out of the box solutions to the people in my discipline who didn't realize that there was a solution to their problem in somebody else's box. To my mind, doing systems thinking requires that problematic dynamics and feedback are part of the thinking. Did you look at the bus problem in session 0, whoever wrote that?
Yeah, this is Paul again.
Yeah.
I did, and so the first thing that problem I have is, and I think this is the difference in perspectives, but I think of systems thinking as requiring a problem where the problem is expressed as a pattern over time of some variable that's of importance to you or to whoever the constituency is. So, growing populations growing beyond the world's carrying capacity. That's a dynamic that probably most of us are concerned about. Or the rise, warming of the planet, or maybe to bring it closer to home, maybe dynamics of arguments I have with my spouse. Okay, so these are dynamic problems, things that something important to me is changing over time. And so that's the problem statement. And then what I think systems thinkers do is they search for system structure that could be causing those dynamics. And that structure must include feedback loops. It must be endogenous. The causes of the and not to say that this is the only way to look at the world. It's not, but it is the systems thinking way of looking at the world, to my mind. So that's the way I define it. And so in the bus problems, I didn't see a dynamic problem statement, and I didn't see feedback incorporated in the solutions. I saw the bus problems as being a pretty good approach to defining what the system boundary is. So in talking about system boundary just for a second, the way I see systems thinkers applying the boundary is, first I start with a dynamic problem of interest or concern. I then incorporate in my thinking those feedback loops that exist in the real world, or that I believe exist in the real world, that could be contributing to those dynamics. And my boundary is around that set of feedback loops and the variables that they contain. And that's how I establish my boundary, is those things that are relevant to the problem of interest, the dynamic problem of interest. So I found the boundary discussion in the bus problem to be very similar to what I just said, even though there weren't dynamic problems, because you were talking about looking at how to look at the inside the bus or outside the bus, the systems in which the bus was involved. That was very very close to what I'm saying, but I have a slightly different take on defining the boundary. It encompasses whatever is in the world from any discipline, from any perspective, that is relevant to creating the dynamics that I'm concerned about. So that's how I tend to define boundary.
Okay. The loops, the causal loops and the feedback come in the operational and functional perspectives, because that's where something's happening. And in the bus case, we looked at the reason why the battery was discharged was a broken feedback loop.
Could well be. Maybe I didn't think about it. I watched the 2 hours before the session today, so I didn't have a thought. it wasn't clear that the feedback loops weren't drawn out that I could tell, and also the dynamic problem wasn't presented. So I think you could look at the bus problem. It may be very, very well. I've had problems before that, on the surface it didn't seem to be a dynamic problem, but I could reframe my perspective and I could find a dynamic problem there. And I've also found that I could reframe my perspective and find feedback loops. So it may be that I have a very limited perspective of the bus problem right now because I just saw the video once. So
Okay, I didn't. If I remember, I didn't actually use the words broken feedback loop, but we talked about the battery charges or the battery's discharge, and the alternator charges it, and we've got to find out why the battery.
Yep, there's a balancing loop there. You're right.
And so the loop is broken, and we've got to find, and the problem solving process is to go down through all the components or go down through the system to find out why the loop is broken.
Yeah. So I hope you don't mind me bringing that up. That was just an observation I had.
No problem. No worries, as they say here in Australia.
Joe, do you have a comment for us?
So actually, I was responding to Dr. Kasser's request for application in another field. And I just, if I could, share my screen because I actually have pictures.
Yep.
These actually come from a paper with an Australian co-author, strangely, Mahmoud Afatnam-Ashnik, for those who might know him, currently at University of South Australia. But this actually comes from, I used to run industrial facilities, shipyards with thousands of people. And, the typical open loop response is you have some sort of problem in production. You decide you've got a flaw, so you go off to figure it out. You determine you actually had an error. You do an investigation. As a result of that investigation, you specify corrective actions, and there's usually 3, something for the trade, something for the supervisor, something for the quality inspectors, and then everyone moves on to whatever is next. And in this particular case, what drew me to draw this picture the first time was we kept on having the problems, and it was like, well, why is that? And we wanted to blame the workforce for not doing their job. We wanted to blame the supervisors for not supervising properly. And we wanted to blame the inspectors for not catching it. And I said, well, maybe not. Let's just add one additional step to this loop. And I'll shift to the other version of this picture. In a sec, let me there we go, get the mouse on the damn page. Excuse me for losing my mouse. There we go. So, okay, let's just add, initially, we're just going to add one step. And that is, as a result of all those corrective actions, the process is now longer and requires additional people. And as soon as you do that, you start introducing the opportunity for more errors because we haven't changed the work standard. We haven't changed the expectations for timely delivery. And so you have the opportunity for more errors. Well, now you can see you get more errors. You get another, and you begin to work around the loop. And let's add 2 more perspectives. This is only one shipyard of 4, and the other 3 send us their errors and their corrective actions, and we send them theirs. And there's also a regulator, and the regulator sends us inputs. So we're adding more and more steps and more complexity to the situation, but we have not changed any of our work standards. We've not changed any of our expectations for the budget or for time. So you get this snowball effect. And so the question became, okay, so how do we approach this? And by means of this picture, basically convinced large chunks of the organization that we had to strip out the accretion of requirements and get it back to the simplest things we could do in terms of direction for the workers, directions for the supervisors, directions for the quality folks, and see if that would work in reducing the error rate. And of course, to me, no surprise, the error rate did go down. Huge surprise to many of the leaders, other leaders in the organization, because they had viewed all of those additions as necessary without understanding the systemic effect of that. And Mahmoud and I published this in one paper because he was interested in the mathematics of it. I tend to be interested in the practical. Mahmoud is very interested in, can we develop a model for it?
Well, this is really interesting, but I see something that might be missing.
Okay.
Once the error has been identified, the information should be sent back so that it's prevented from occurring in the future. Is that
so
somewhere?
So that's actually in the one or more additional actions there to prevent a reoccurrence. That includes sending it back.
Okay.
And that's buried in that block there. We would usually attempt to revise the written instructions for the workers. That would be the additional trade actions are added to the technical instructions. But so that's in there, yes.
So that wouldn't actually change the process. It might increase the complexity of the manufacturing process, but that would be a bad way to implement the solution.
What it did is it added and started gradually, but over time you get a significant volume of paper to describe what the worker has to go do, and our effort was to distill it down to the minimum required.
Yep. Have you ever watched Charlie Chaplin's movie Modern Times?
Yes.
I think all quality control inspectors should be required to watch it.
So I think we're going to need to take a little break here so that we can prepare for the next session. Give us a minute and we will be right back. Thanks, Joe.
Thank you.